exponential functions. For exponential functions, the base is a constant, and there are some conditions on the base, these. So the base has to be a positive real number, but it cannot be equal to 1. And x is the power. So which of these is an exponential function? That one's fine. The base in this one is 3. It's not minus 3. It's like this. So the base is a positive number. The base here is negative, so we can't have this. It's not exponential. The base cannot be equal to 1, so this is not exponential. This base is fine. We've got a quarter. This one's okay. This one does not have a constant as the base, so this is not exponential. The base is pi. Pi is a constant. Yeah, this one's fine. The base is a positive number. It's not equal to 1. That's fine. And you can have any function of x as the exponent. In this one, e is a special mathematical constant, and we can get e from here, or we can get e from here, e to the power of 1 there. So the base is a constant, x is a power, and the plus 4 there is just a transformation of some sort that's been applied. So yeah, that one's fine. When looking at graphs, if the base is between 0 and 1, we get a decreasing function. The gradient is negative always. Or we can call this a decay curve, an exponential decay curve. And on the x-axis, we have an asymptote. We can see the curve is approaching the x-axis but never reaches it. And the equation of that asymptote there, the equation of the x-axis, is y equals 0. And if the base is greater than 1, we have a growth curve where the gradient's always positive, so it's increasing. Again, we have an asymptote on the x-axis, and the equation of the asymptote again is y equals 0. So for a decreasing function or a decay curve, if the base is between 0 and 1, like we have here, 1/3, I could write the 1/3 in this example as 3 to the power of minus 1, and then expanding the brackets, we get y equals 3 to the power of minus x, because we're multiplying the powers together. So a negative value here also indicates that you could possibly have a decay curve. So we have the graph of 2 to the power of x. So for 2 to the power of x, when x equals 0, we have y equals 2 to the power of 0, which is 1. So the y-intercept is 1. So if we want to sketch f of x plus 3, where our function is 2 to the power of x, then we're sketching this graph. The plus 3 means we need to move the graph, or translate it, in the positive y direction by 3 units. So the original asymptote was on the x-axis. If we move it up 3 units, so that's on y equals 1, y equals 2, y equals 3. So I need to put 3 on the graph here, and the original y-intercept was 1. If I increase that by 3, it's now 4. Part B, in this one we're replacing x with x plus 3. If we had f of x, it's now f of x plus 3, which means we're looking at a translation. It's in the negative x direction by 3 units. So the 2 to the power of x graph, which is this, I'm going to move that to the left by 3 units. So the graph should look something like this. when x equals 0, y is equal to 2 to the power of 0 plus 3, which is 2 to the power of 3, which is 8. So this time the y-intercept will be 8. Part C, we're doing a times 4 stretch in the y direction, so any y coordinate will be multiplied by 4. So the y-intercept is 4. The graph still approaches the asymptote, which is on the x-axis. In this example, we have to calculate the values of p and q. We're given the coordinates of 2 points on this graph. If we substitute the coordinates in, we have simultaneous equations which we need to solve, and solving gives p and q. One method for solving would be to take the equations and to divide them. When we're dividing them, the p's will cancel, and then you can do something with the indices there. You've only got q left in the equation. You can solve it to get 1/5 for q, and take the value of q and put that into this equation, work out the value of p. For practice, try these questions.